This is a joint work with Nathan, so it's again a checkpoint attached. So today we're going to talk about the goodness of fit for a multi-class prediction. At first, who am I? I'm a senior data scientist for TRST AI. TRST AI is a startup that we're doing data science omitting. Basically, we're doing sensitivity analysis and ensuring that that AI systems are reliable and won't do any bizarre stuff. In this point, we're focusing in the financial market, but we have more. I have a PhD in applied math from the Technion, and although my supervisor she's emeritus from the Tel Aviv U, and so my interesting in data science, math, algorithm. If any of you wants to contact me for anything, feel free. This is my email. Feel free to contact me. Okay, so where can we find the multi-class? Like the most trivial thing is you might argue that it's in the e-commerce. Like you go to a website, you can buy a shirt, you can buy pants, you can buy shoes. Those are different target, and so you want to score them. And another motivation is from the cybersecurity, because before we saw one type of attack, but as earlier mentioned, there's many different ways to attack cyber. So basically, we need multi-class, and each class is different. The motivations for me was the IoT robots. I was working as a consultant. For detecting which kind of grain were grounded. I know it sounds totally non-AI, but there was a problem, they don't know, and so they had lots of classes. They had coffee, they had beans, they had nuts, and they want to know which one is getting grounded. And it turned out to be a hard question, and this is where I got in the picture. And at first I thought it's trivial because everybody know that, and I started Googling it, and all the answer I got were not satisfactory, but somehow we made that. Another issue that you might think about is predictive maintenance. If you bring into the wrong technician with the wrong gear, it can cost lots of. It's going to be very unpleasant. So, why do we care? First of all, there's the issue of fair AI, and that is getting really strong, and the multi-class is a huge issue there. Detecting weak segment is very important. Robustness of the classifier. And of course, if you're doing adversarial example, if you spotting out that one of those classes for some reason is the classifier mismatch it, it's a very good start for your adversarial example. So let's reveal a few methods that are known. There's a one against all. Usually when there is one important class and the rest, like you say that malicious and non-malicious, this is one way of attack. It usually works well when you know which class is important. If you don't know, it doesn't well. So then they have the second approach. It's all against all. Is just like Fight Club. When they arrange, when everybody is arranging in pairs, all possible pairs, and each pairs are just fighting each other, and then you average things up. So this is what. The second method is sometimes you can do hierarchical. Like let's say here, like a movie, it can be a comedy, and then it can comedy, action, and it's hierarchical, and it's one approach. Another approach is we assume that all the classes can be somehow embedded in some kind of a latent Euclidean space, and then your multi-class problem becoming a regression problem, and everybody's happy. If anyone knows how to do this embedding, I'll be happy to learn, because usually we have no idea. So, our assumptions, we don't know the prevalence. Like, we don't know if there's one class is more than the less. We have no idea. And we don't know each hierarchy. We don't know the embedding. An instance must be in one class. And there's one thing that distinguish a good and experienced data science and a beginning. A beginning data science would say, okay, no problem, let's ask the domain expert. But then when you learn your expertise, you learn that the domain expert don't give a damn about you. So you can ask, but he won't be available as way you wish he was. So our approach is that we know nothing. Okay, let's start with the binary case. Binary case, one positive, you're negative. And in the binary case, we all know those type 1 error and type 2 error. A type 1 error when a male gets diagnosed as pregnant. A type 2 is when a pregnant woman is diagnosed as non-pregnant. I think all of you saw this slide somewhere. Okay. The confusion metrics. It's kind of one of the basic, which is a true positive, those who you predictive positive and they are positive. A false positive, you predicted positive but they are negative. False negative are predicted negative but they are positive. And true negative are predicted and so the main problem is that our data is unbalanced. So basically, many things are not suitable. Like many methods are mounted, and the accuracy might mislead us. So basically, let's go to those, reveal those cases. What is accuracy? Accuracy is how much we write. Recall is if we predicted positive, it's real positive to predict positive. Precision, if we predicted positive, real positive. Specificity, if it's real negative and predicted negative, given predictive negative. And NPV, negative predicted value, which for some reason doesn't have a nice name. The recall has another name, sensitivity, but the NPV doesn't have any name. And since we all love pandas, everybody loves pandas. And so basically we can, if we have an accuracy function, we can rewrite this in pandas if we don't. Okay. Okay, let's do a little bit recap about means. This is the algebraic mean, just taking divided 2, the geometry thing, you multiply and take the square root. And you remember the harmonic mean is going to be up next. And we have the harmonic mean, and the F1 score, as probably all of you know, is the harmonic mean of the recall and the precision and harmonic. So why do we take the harmonic mean? This is one of those classic job interviews questions.
The smallest of the three?
Thank you very much. The harmonic mean is the smallest of the algebraic, geometric, and harmonic, the smallest one. So basically, taking the harmonic would be a good bet. Okay, let's ask if we have only a negative predicted. We predicted our target value is 0, our predicted value is 0. What would be our accuracy?
100%.
Yes, and what would be our F1 score?
100%.
Anyone else?
No, it will be something.
Anyone else want to guess? Say one. Anyone else want to give a try? How the way scikitlearn? And this would be 1 and this would be 0. And anyone who's doing testing in AI should realize that. And the interesting thing is that there's a discontinuity. This discontinuity might be a little bit problematic in some cases. So beware. Anyone who's familiar with scikitlearn, and there's a F1 0 and F1 1. which is taking kind of a generalizing, is that the F11 is what we know, and the F10 is the specificity and the negative predicted value. And the reason we take that is that we want to see both for the negative and the positive. And Mathew correlation coefficient. Brian Mathew was a biochemist from Australia. He's from a suburb of Adelaide. And he decided that defining this metric would be the geometric mean of the predicted and the true positive predicted a positive, and if we take this math and we take the determinant of this matrix, we get a classifier. There's a few papers that test the F1 and the Mathews, and usually in most aspects the Mathew is superior. So if you're thinking which one to use, I recommend to take the Mathew. So let's remember why you're taking the determinant. If you remember that what is the geometric meaning of the determinant is the area of 2 of 2. So basically, if we have this matrix, we want this matrix to cover as much area as possible. This is the geometric meaning. Remember that in the multi-classes, this intuition would be very useful. And if we're taking the correlation, the Pearson correlation between the target and the predicted, we're getting again the Mathews, which is a nice result. And vice versa.
It's vice versa. It's vice versa. He calculated correlation and obtained it.
Yeah. This is Mathew calculated correlation, got the Mathews, but it's a nice result. And there's another metric, which is the AUC of the RAW curve, and just you take the threshold and you play with that and the area. It's a little bit off scope here, so forgive me that I'm going to not go more of that. Okay, let's start to think about multi-class. We came here for multi-class, not to see a recap about two classes. So we want a multi-class metric, and this metric, first of all, it's got to be classes renaming. If you rename a class or the order of them, you want the same result. If you want intuition, if Do spoke about GNN, one of the main things about GNN that you want to be invariant to nodes order, and it's the same here. Think about those classes as kind of nodes. You want, if someone is playing with them, you want the same result. And the second thing is that you want to flip the target and the predicted. Why do you want that? The reason that you want that is that it's the equivalent of a non-bias classifier. Like if you want to take a non-bias regressor, and there's lots of statistics, good stuff that occurs if you take that, and you want the same for those classifiers. If you want this full analogous, you need to use the second property. Otherwise, it won't happen. So the multi-class has a confusion matrix as well, just like you think it would have. And well, the first approach is taking F1i, taking for each class. I can take some kind of a harmonic mean of the chance of predicted I and real I and predicted I. It's kind of one against all approach. And I have this Fi. If I take some kind of a reasonable average, I think I implemented in the code with harmonic mean, but you can use any average that you like, which we stated in the paper some way how to define a reasonable average, but if you want the algebraic, harmonic, everything is good. Geometry, everything is good, or if you want to pick your own one. Okay, I'm sorry this slide isn't, the setting here is a little bit, yeah, of course, it's actually it is Nathan's fault. Nathan made this slide. Well, basically the chi-square. What is a chi-square? Forget about formulas. We have two vectors, categorical, and we want something equivalent to a correlation. But we don't have a correlation for categorical values. So what do? We have some kind of a association. What is the association? It means that if you're getting it means if two values are somehow associated, like if there's those two vectors are independent, it means that they're not associated at all. And if they're dependent, so basically you can predict one from another, it means that they are associated. If any one of you is doing EDA, which I guess every one of you is doing it, EDA, I think using for categorical features the association test is a good idea. So taking the chi-square, it's a way to measure how much those two vectors are dependent, and we can go the Kramer. Kramer was a Swedish statistician, and he said, okay, let's see how much that the target and the predicted are related. It gives some idea, but not perfect. Why not perfect? Because all of the statistical measurements are you basically want to reject hypothesis and not be sure, and here you want to the other way. So it's a good idea, it's a good approach, but not good enough. Okay, so and this is the main result of our work. We took the geometric mean of a metric. The entry ij metric would be the geometric mean of the I predicted A and the predicted J for I. We have this matrix. It is symmetric matrix, but not a positive matrix. And if we take the determinant, we get the generalized Mathew correlation. And why are we taking the determinant in more than why do we take the determinant? The main intuition for 3 dimension is volume. In more than that is hypervolume. It's a little bit hard to plot a 4 dimension, so forgive me. Okay. Multi-classes. Desirable metrics. Which desirable? If we're taking the average F1i, it would be cool. It would be, it's a good bet. If you're wondering for a multi-class, the F1 good way. The Kramer would be okay. The general Mathews, they were doing it. We can do the all against all, although it's kind of, I don't like it that much because it's a little bit overkill, and you don't realize if you have like those some classes are bullied other classes. And in the Mathews, you can really see that. Like if one classes doesn't get prediction or Mathew realize the other metrics would be less sensitive for that. Okay, since we're in PyData, I need to show you a Python code, right? It's part of the deal. And basically, it's a simple code. I program it, so it can't be that hard. So basically, I'm using the harmonic mean and the geometric mean of SciPy. And here I took first I calculated some kind of a matrix, and in the general FI, I just took the trace. I'm interested only in the diagonal, so basically you might say trace. And in the Mathews, I'm taking the determinant. And Kramer, it's really implemented in. It's implemented. I think there is more compact way, but I saw it, but there was something that I didn't like the way it was from out of the box, so I wrote those 4 lines. Any question about the code? Can see. It's a little bit dark. Okay, so let's sum it up before entering the questions. Basically, we saw the why multi-class. Then we had a little bit recap to 2 classes, and then we defined what we want to see in multi-classes, and we ended up in a few examples of a multi-class metrics, and that's about it. Till your question, feel free.
I don't think I follow you 100%, but we're talking a lot about determinants, and I'm kind of concerned. Is there a situation where we have like non-regular?
Non-rectangular? Well, actually, you don't. You don't have such a situation, and the reason is that if the numbers of classes in your target doesn't match in the number of classes in your predicted, then something is wrong. Because it either means that there's some classes that didn't get any predicted, and then you just added a 0, and then you'll get 0, and just like what you want. And the second option is that you predicted something that was not in the target, and this is not a desirable thing either. So basically, you can't get you can't get a rectangular because we assume that you're not adding and not omitting any classes, because it doesn't make any sense.
So you answered almost what I asked. It's not regular. So if I have a repeated row, so the same classifications for different.
What does it matter? So if you're having such so basically, it means that you're classify. Think about that in a classification point of view. And if you have something like that, it means that you're doing a lousy job.
In one case.
No. It means that you can't. Predicting to the J class is just like predicting to the I classes, and you assume that your prediction makes sense. So basically, you kind of assume that you're targeting I to I, because otherwise it's you get the metric would give you a lousy score as it should. So basically, your answer is. 2 categories of 2,000. No, we're not talking about the minor two of those. We're talking about the entire row. So it means that it's either you're not predicting to those classes. You can't distinguish. If you can't distinguish between them, it means that something is wrong with your prediction. So you don't want that either. So getting a 0, it would be
No, but aligns, theoretically it aligns with the idea that the model simply stops.
Yeah, basically it means that
because it's making, from the determinant perspective, it's mean that the volume of the parallelepiped is 0.
Yes.
And you don't want that.
Model sucks simply.
So basically it tells you that you're in a crappy situation.
Perhaps it may happen, but it means that you didn't.
And you want to get a lousy score. You want to get a lousy score in such a situation, because it's not something that you're desired to.
The code you showed is something. Those are simple pieces of code,
Yeah.
but you do have use case that is your people don't use, like in your case, multiple classes. So, are you about to release that code?
This one? Yeah, I can. It's in a Git. It's not on Git. You can, if you want, you can. You can.
License?
Hmm?
Under what license?
Nathan, what's license? The license would be as kindly, and you can use it. You can use those 8 lines of code as much as you like.
That's good. Thank you.
How will you give some weight if the model predicts I in 60% confidence against the model predicts I in 90% confidence if I want to do so?
I don't know, because the main thing in multi-class, instead of 2 classes, you're not focusing in one class. Like it's the main focus of this work is that you want the holistic way. You want to see the entire classes, not only one classes. Maybe but in a way you're right. If there's one classes which sucks, the model would give you a bad score, and you want that. And the reason that you don't want one class that is getting bad score, it usually means that you have a fairness problem, and you don't want that. Trust me, you don't want that. No.
In order to derive uncertainty, you should follow the DNN protocol. Simply take one test and throw it 1,000 times.
Yeah, you basically say that the prediction is the highest percentage. Don't mind the percentage that the model gave you.
Some sense, yeah. Anything else? Okay, yeah.